רקורדים.
אני פשוט ללחוץ על כפתור.
אחד מהמספרים, לא משנה איזה, זה מדליק את המצלמה, אם היא קבועה.
תודה רבה. אוקיי. So any questions about last time? Last times? Okay. So I want to give some more examples of functors and equivalences, and then we'll go to the next topic, which is unit tests. Did we discuss two functors in the Excel? So that's it. So I have several interesting functors from the space of the category of vector spaces to its set. So you probably remember the function v goes to v times of v. This will be discussed. Yes. And you can add here how many bits you want. The n stands for power. And you probably remember that inside the let's start with this second tensor power. Also, one way to think about it, if v is finite dimensional, it's bilinear forms on v. On v star. If v is finite dimensional, then this is the same as bilinear forms on v star. You know, yes. So in bilinear forms, you remember that they are symmetric and they are antisymmetric. And here in the tensor product, you also can define symmetric vectors and antisymmetric vectors. So symmetric and tensor product generate the vectors like this. So symmetric vectors are combinations of vectors like this. And antisymmetric vectors are combinations of vectors like this. Or in other words, you have the action of the group S2 on this space. Action of the group on a space is clear. Yes. And so the action is just mapping V tensor W to W tensor V. It's also two different vectors in the same tensor product. And you can consider even vectors, so vectors which are equal to the S, what happens after S2 act on them, and odd vectors, vectors which are equal to the negative what happens after S2. Now you can generalize this to this guy. So you have S and V, which are even vectors, not even symmetric vectors, vectors which are invariant with respect to any commutation of all these guys. And you have lambda and V, which are vectors which are antisymmetric. So when you flip two guys to neighboring guy or to any in two guys, you get a minus sign. And you can ask what happens when you do a general commutation, then you get some sign, which might be not minus sign, might be a plus sign, depending on the permutation, and this is a sign of the permutation. Okay. So to be on the safe side, it's better to do all this stuff in characteristic 0. So the base field should be in characteristic 0. You can define all this stuff for positive characteristic, but then you have several different ways to define it and getting several different answers. So for now, you can repeat whatever I said, and you will get some reasonable answer, but you can change it a little bit. So here it's a subspace. You can also consider the quotient space. So vectors here modulo equivalence relations that make two things the same when you switch to coordinates are just the same. And these two things are like, yes, in characteristic 0, it's equivalent. You can consider the subspace and the quotient space, and they're canonically isomorphic, and positive characteristics are not. So let's for now assume okay, 0. there is something to do in positive characteristic. So these are two nice functors from Vec. And now here, if you have only two Vec, then one of two copies of V, then basically everything is either even or odd. So of course it's not true, V tensor W neither even or odd, but everything can be uniquely written, take basic difference in two, so everything can be uniquely written as a combination of even vector and odd vector. And here it's not true. There are lots of other stuff. If you want to compute the dimension, you see, so what is the dimension of odd stuff here? So let's say that the dimension of V. So odd stuff, not all terminating or whatever, it's called stereo power of V. The dimension is a number of subsets of size D inside N. In particular, if D is larger than N, it is 0, and if D is equal to N, it is 1, then it can become larger. And if you take, sorry, no, I say everything oppositely. Subsets of size N inside set of size D. And this guy, its dimension is a number of multi-sets of size N inside a set of size D. So it's never 0, unless D is equal to 0. So you always can have more and more symmetric powers, but still in some number, and if you consider the dimension of the entire thing, it's much larger. It's like D to the power N, which is way larger than what I said. So, in fact, there are plenty of things in between, and those are called the Schur functors. So, you all know what is the representation? Somebody don't know? I already said it in a different language. So, representation is an action of a group G on a vector space W. So, linear action, and element G gives you a linear transformation, and it satisfies the axiom of group action. So, in other words, you're homomorphism G to N. So suppose you start with some, so representation will often denoted by a tuple, a pair, pi W, pi is like the action itself, and W is the space. But then we sometimes think about the representation as this mapping, but sometimes think about it as space W, as usual when you have like vector space. So vector space is a tuple, yes, you have space and addition and multiplication by scalars, but you usually ignore all this stuff about the space. So now we have a representation pi of the group Sn. And then you can consider home over Sn. So the collection of all representation in the category. So homomorphism of representations is just a linear map that commute with the action of the group. So you can consider home over Sn from pi to V to the nth power. So this is also a representation of Sn, because Sn actually need by changing the order of the coordinates. And this will denote by, say, Schur pi. So Schur pi is functor. As usual, I don't really define functor, only define what it does for objects, and you can guess what it does for operators. From Vec to Vec. And in this construction generalizes both in construction of symmetric power and anti-symmetric power and lots of things in between. So usually we kind of most care about these two edges, so symmetric and anti-symmetric. So symmetric power, the Schur functor corresponds to the trivial representation, and the anti-symmetric power, the Schur power. the show functor corresponding to the sign representation. The sign representation is a one-dimensional representation where each element multiplies the vector, like the vector in one-dimensional space, by sign, by its own sign. Is it clear? Is it not clear? Everybody abstains?
These functions are not additive.
Yes, yes, yes. Or not additive, starting with n equal to 2, because v goes to beta times v, so obviously not additive functor, it's kind of quadratic. We don't add map sum to sum because like taking square. If v is one-dimensional, endomorphism of v multiplication by 5, then you get endomorphism of v times of v, which would be multiplication by 25. So not homomorphic. Okay. So now if you did some course in what do you call it, differential topology or analysis of manifolds. So you define the notion of a vector bundle, and then you probably define the notion of a tangent bundle, which is some specific vector bundle, and then you have constructed lots of bundles out of it. So the bundles of bilinear forms on the tangent bundle, or symmetric bilinear forms, antisymmetric bilinear forms, and polylinear forms, like the top differential forms or some other differential forms. And you can ask, so do you actually need to define it each time from scratch? So you have some construction with vector spaces, then you upgrade it to a construction with vector bundles. So what I would like to say is that if we have functor f of vector to itself, and let's put it in some reasonable framework, so let's do vector over R, because we're talking about real manifolds, and let's say it's a finite dimensional because it's what we care about. So we have functor like this. We want to upgrade it to functor from vector bundles to vector bundles. So any opinions whether it's possible to do or impossible to do in general?
In terms of product operation of vector bundles, so you can just repeat all this stuff.
So all the true functors we can do. And because we once need to define what is the tensor product of vector bundles, and then we can do a little bit annoying that we'll have to define what are tensor product of vector bundles, but you don't know what to do. But is it true for any possible functor? So the answer is almost. Any reasonable functor, yes, but you need to add some condition because you're working in topological framework. Yes, you're working vector bundles is something continuous, so it's a topological space. Morphism between vector bundles are continuous maps, and here you're doing something completely algebraic. So you need to add another condition. So we define condition is continuous. So I don't define the general notion of continuous functor. There is some notion like this, but it does have nothing to do with this notion, but not generalize this continuity, so ignore it. But only in this context. If f from let's call it f x VW. W is Okay, so F is a functor, so we have morphism to morphism, so we have two vector spaces, we have morphism between them, that are linear maps. This is a vector space, a fine dimensional vector space over R. It's a natural topology, it just can identify it with Rn, it's topology from there, and obviously it will depend on the identification. So you want this map to be continuous. Once this map is continuous, you can call the functor continuous. Again, this is notion in this concrete context of this concrete category. And then any continuous function can be upgraded. And let's call it f(x) and for bundles over x.
Okay, what is the topology of the
Home. So this is fine dimensional vector space, this is fine dimensional vector space, the home have nature structure of fine dimensional vector space over R. Any fine dimensional vector space over R have topology, nature topology. For example, you identify it with Rn for some n, and takes topology from there, and nothing will depend on the identification. So basically, it's a unique topology, which is a linear topology. So the addition is continuous and multiplication by scalar is continuous. As a map of that is beautiful. And addition also. Then together.
Could you give an example of non-continuous function?
What?
Could you give an example of non-continuous?
They can try, but maybe a bit offline. It will be something weird. So you can starting with choosing a basis of R over Q and then doing some weird stuff. Maybe this was a yes, I should think, but I'm pretty sure that this one is going to be very good. Okay. Yeah, do I want to give some other examples? Yeah, maybe. So you can use this to reconstruct maybe all the stuff that you already know about vector space, about vector bundles. So tensor product of vector bundles, symmetric powers, anti-symmetric powers, and all, or the Schur functors if you want, the notion of differential forms, Riemannian metrics, all this stuff. So another thing that usually is not taught, but it's a good idea to teach it, is the notion of densities that you can also reconstruct for this. So I want to define the functor. A functor of densities. Densities. Then of a vector space V. So come back to vector, and you take any vector space to a one-dimensional vector space. So it's probably a contravariant functor, but it doesn't really matter. So how we can think about top differential forms or top forms? It's so you form the top V vector of V. Yeah, fine dimensional here, yeah, as before, fine dimensional. So one possible definition, the polylinear antisymmetric forms, but another way to phrase it is collection of all maps. I don't see base to R, such that P of GB equal to that G. Okay, so if we have two bases, and we have the matrix G that might be other name, you see it, transform one basis to another, and then the value of this function will be multiplied by the determinant of Yeah, so usually we define forms not like functions on bases, but functions on n tuples of vectors. But if the tuples are not basis, the tuple is not a basis, then the form have to be 0. And so there is no really information there. And usually we want it to be just polylinear. And here we say something like much more general, what happened with any two bases and not just combination of like linear combination of two vectors, but you all know it's the same. Once you know that the mapping is polylinear, then you know that when you have any transformation between the bases, you multiply by the determinant. So of course I simply defined here top differential forms. There is this friend of this guy, which is lambda n of b, and this is equal to lambda n. Lambda n, you remember what's lambda n? This is equal to lambda n of c star. So of course it can be confusing between these two guys. I hope you will forgive me. And so now we want to define densities. B. The same thing, but here I want absolute value of the determinant of G. And so this is also a functor. Any linear transformation between two vector spaces gives us a linear transformation between the corresponding. So probably it's better to restrict the dimension of your spaces. Here we say fine dimension vector spaces, but maybe better to fix the dimension and consider only this category. I think you can do it in general. There's no notion of determinant of rectangular matrix, so you can do it in general. And so, but all what I said here also works for functors from the category of vector space of a given range. And each time you have two vector spaces, you can construct, or each time you have vector space, you can construct this weird one-dimensional space. And if each time you have two vector spaces and a map between them, you can construct a linear map between the two one-dimensional spaces. And if it's vector space and itself, then you get an endomorphism of a one-dimensional space. And the endomorphism of one-dimensional space is just a number because you just multiply by a scalar. And this scalar will be the absolute value of the determinant. Here it will be the determinant, and here the absolute value of the determinant. And this is nice one. So when you think about one-dimensional vector spaces, it's kind of useless, yeah. So there's only one-dimensional vector space, so at least they're all isomorphic. So why would we care? But functors for the category of vector spaces, so n-dimensional vector spaces, to the category of one-dimensional vector spaces, this is not a trivial thing, because although there's only one non-trivial vector space, but up to isomorphism, but when we do functors, we not only care about isomorphism classes, we also need to say what happens to morphisms. So there is some information hidden here. And when you do it, so you get this construction, which is already by itself non-trivial. And the nice thing that it gives you, you can apply it to vector bundles, and you can apply it to, say, the tangent bundle. So for any variety, manifold, you can take its tangent bundle, and then you can take the bundle of densities of the tangent bundle, which is just called the bundle of densities. And it looks very similar to the bundle of top differential form, but a little bit different because of this absolute value. And if you recall in multivariable calculus, you probably been taught the formula of changing of variables, and you remember that there is some determinant of the Jacobian that pops out. But it's not just the determinant of the Jacobian, it's the absolute value of the determinant of the Jacobian. And then if you just do like in the analysis of manifolds, you usually been told that there is a way to integrate top differential forms. But over what you can integrate top differential form, you have to choose what's called cycle. So you have to choose some variety or even the entire variety, but together with orientation. If you don't have orientation, you can't integrate top differential form. Because the way to do it, you identify some pieces of your variety, of your manifold with Rn, and then you just take the integral in Rn. And if you choose two different identification, you will get the same number because of the formula of changing of variables. But
Not the orientation.
yes, if you really want to get the same numbers, the choice has to be orientation preserving. And it sometimes look disappointing. You want to integrate over the manifold itself. You don't want to choose integration. And why won't you be able to do it? You can integrate functions over R. Why you have to choose orientation in order to integrate a function? So, okay, you can't really integrate functions because functions are not density. When you change the variables, if you just consider them as a function and without multiplying after the value of Jacobian, then the integral will change as if you will, how do you call it? Scale everything by 2, then the integral will become twice more. So you need, when you scale everything by 2, you have to make the function twice lower, like it's a density, so you have to spread it, so it becomes less dense. But so the actual object that you can integrate is a density. It's not a function, but it's also not of differential form. So if you have a density, meaning a section of the bundle of densities, then you have well-defined notion of integral. How you do it? You have a manifold, say F. No, maybe we will get to this material in the cell hour. So you have manifold M, you have, and you cover it with something homomorphic to Rn, you maybe do partition of unity, whatever, you just want to integrate over one piece. So you have Ui, which is homomorphic to Rn. You have your density on M, you restrict it to Ui, or multiply it by some function, blah, blah, blah. You have something that you want to integrate here. You use this identification in order to consider it as a density on Rn. And on Rn, densities are the same like functions because you like tangent space of Rn in any point is Rn, and the bundle of top differential forms, so like lambda or omega n of Rn, like identified with R, and canonically identified because here you have basis, canonical basis, and then also densities of Rn is identified with R. Again, because you have basis, so you can ask what your function given this basis. And then function, the densities are just functions, and then you just integrate the function on array. And then you can ask what will happen if you choose two different identification, and the answer, the integral will not change because of the formula of changing of variables. And these times you don't need to preserve orientation, because even if you do not preserve orientation, absolute value of determinant is what you get. So this is some kind of a way to correct the notion of short differential form to a notion that you can actually integrate. So this correction maybe make it worse from some other perspective, because of the probably two ways you want to think about integration. One way is integrate over a measure like this, but there's sometimes also meaning to think about directional way. So in one variable, you can integrate over the interval from A to B, or you can write integral over the subset. This is like probably more related to measure theory, and this is kind of more like Riemann-like integral. Of course, both of them you can do Riemann and Lebesgue. But here, when you change A and B by order, you get negative sign because you just remember the direction where you integrate. And here, you just integrate over a set. So if you change A and B by order, you probably get an empty set, so you get 0. But anyhow, you have the same set, it doesn't have direction. So densities, this is integral of densities, and this is integral of top differential forms. They both have a right to live, but they're slightly different. Okay, איפה המחק? הנה המחק. So one more example before we go into another unit.
Can I ask a unrelated question? Is there some relation between the pullback of linear mapping differential force between the pullback learned in categories? Or is that just a coincidental?
Oh, so can you say the pullback of the differential form?
Mhm.
So there are probably many relations, but we need to fix the context. So what we pullback in categories, then we talk about pullback of the over category. And you also have pullback of vector bundles. If you have a map between two manifolds, you have notion of pullback of two vector bundles. And what is the pullback of differential form? So if you have P from M to N, then you have phi alpha star of omega to or omega Kn. This is a new bundle. And we map from this guy to omega K. So this is a pullback of differential forms. I think this is the correct direction. This map, so it's also called. Okay, so for the next example of functor factor of equivalence of categories, I want to define a new category, ban G. So given ban G of, so given a manifold M and the group G, a Lie group G say, we can define ban G Fm to be so its object. As usual, I would define the objects and you will guess what are the morphisms. The collection of all spaces say X together with an action of G and the map to M such that any fiber is a simple type. So this map should be it should be a fiber bundle. So it can locally, you remember locally it looks like the fiber times the base. And the action of each fiber, G acting on is the G principal space, so it's simple time. Korean time. Okay, so another category of kind of vector bundles. So we before had covering spaces, vector bundles, fiber bundles. So this is so they're usually all special cases of fiber bundles. So it's a subcategory of the over category and subcategory of the category of fiber bundles. Not really sub. It's an additional structure. So, but you have a faithful functor, a forgetful functor. So it's category of fiber bundles, and it is a faithful functor. It's not fully faithful. And on each fiber, you have additional structure of G principal bundle. And here is no example exercise. Given healing from by G and out. The category of n-dimensional vector bundles. So on the first glance, it looked a bit weird because here, like we're talking about n-dimensional objects, and here we talk about n-square dimensional objects. And these are vector spaces, and these are G-length principal spaces. So it's look different. But the categories are equivalent. No, I'm not completely correct. Can I make it equivalent? No, I show here. So I take this category, but I allow only isomorphisms. But in this category, all morphisms are isomorphisms. Yes. And how is this correspondence working? How the function working? So probably the easiest way is to start here and then get here. Go start the function to linear. And what is this way? You start, so let's start first of all with a vector space. To have a vector space, we can consider the collection of all bases of this vector space. GLN acts on this collection. So might be a bit confusing because we have a space V, so we have bases V. So of course GLV acts on this collection because we can change coordinates in V. But also GLN acts on this collection. They're different because V is maybe isomorphic to Rn, but not canonically, and the action is very different. The idea is that once you have a basis, you can make any invertible linear combination of the vectors of the basis and get new bases. So any matrix, n by n matrix, gives you new basis from the old basis. Just you choose it as a matrix to change that. So now if you have a vector bundle E over M, you can consider the collection of all pairs point in M and a basis of the fiber. This collection, in a very natural way, have a structure of a manifold, because locally you can see it just looks like a vector space time neighborhood in M, and collection of all bases is a manifold. I would say it's okay. The very you embed it into V to the power n. It's a nice structure of a manifold, an open set in V to the power n. And so you can locally give it a structure of a manifold, and then you glue everything together, so it's a very nice structure of a manifold. Now also GLN happened by changing the basis. And once you, so this manifold is a G principal space. So this gives you the factor from here. And the factor that okay, maybe we can stop for a moment now. So you have factor from here to here. You start with a manifold, then you replace in the vector bundle, then you replace each of the vector spaces in the vector bundle, you replace it by something much larger by GLN transfer space. Now, how you do the other way around? The other way around it's a bit more tricky. So, what like this? You have vector bundle here. You have G principal space here. Let's call it some name X. And then you multiply it with Rn. And the quotient by equivalence relation comes from GLN. So this is not fiber product. I put the GLN upstairs. So GLN acts here and acts here. So you can construct the equivalence relation saying that G equal to V is equivalent to E G. And maybe I need somewhere to put in those. Maybe it does have. I don't remember what it's called. No, I don't think it does. And once you quotient the equivalence relation, you can see that you reconstruct this function is inverse to this function. And as usual, you don't really need to construct the other function in the other direction. You only need to prove that your first function is fully faithful and essentially surjective. But when you will want to show it's essentially surjective, you will need to at least construct, given a GLN bundle is called GLN bundle, you would need to construct a vector bundle, so you need to do something. And okay, so this is a nice construction, and for me, it was kind of shocking after I understood what it means. Because, okay, when I first studied branch topology, so or even before tensor product, so we define tensor product as a universal object. So what's the tensor product of V tensor W? It's a universal object L such that for any K, or universal object such that for any vector space L, and this map is the same as a bilinear map. V W.
Of any linear function from V and
So this is the same. The linear maps on the tensor product are the same as bilinear maps. And this is very nice definition, and also we have some nice construction as taking V tensor W and spending all of them. But then I knew that spending all of them and quotient by some good research. But then I knew that physicists define tensors in different ways. They choose a basis on V. Usually they just work with one space, and then they want tensors like V times V times V times V. So they choose a basis on V, and then they represent the tensors like these huge matrices, and then they say what happens when you change basis, and this is it. And I always was thinking about this way as the abstract and advanced way, and the physics way, like this technical way that they do for computations with objects. But then I saw this construction, which is, so what is a vector bundle in general? Even it's this band, instead of considering usual vector bundles, you can consider band G for some G. G, okay, G is GLN, but you can also do it for other groups. So this looks like much more general construction. But then I realized that this general construction is exactly what physicists do all the time. But what really happens here? And you have for any. So when you define in the physics language a tensor, so what you're doing, you consider a collection of all assignments that for any basis vector, for any basis gives you this huge matrix. And you have an action of this collection. It's the action of all action of GLN. When you change bases, you get new matrix. So okay, maybe not really ready to explain in details, but basically this more kind of advanced way of thinking is the same like the kind of less advanced way of thinking in base. And this was for me a nice realization. So what this realization also can give you. So first of all, you can immediately ask what happens if I change GLN with some other Lie groups. So for example, what happens if I change GLN with the group ON? Do we have guesses? What will I get here? What is band ON? Exactly. Bundles with Riemannian metric, with a scalar plot. Positive definite scalar plot. If instead of ON you take OPQ, do you all know what is OPQ? ON is square matrices that preserve. Yes, so ON is square matrices that preserve positive definite bilinear form, symmetric bilinear form, and OPQ it's square matrices endomorphisms that preserve some specific bilinear form, which is not positive definite, but it's a signature PQ. And then we'll get bundles with a metric of signature PQ. So you can take SVN, so group of all matrices that preserve an antisymmetric non-degenerate form. Then you will get symplectic bundles with a symplectic form. And you can try to take other Lie groups, and then you will not have such nice geometric understanding into what is band G for other groups, but it's kind of really analogous to this. So you always can think about it as vector bundles with some additional structure, which might be weird. Also, you can have a map between one Lie group to another Lie group. And this map will induce a functor from band T to band H. Yes, so if, for example, you have a map from ON to GLN, standard embedding, and this gives you a functor between vector bundles with a metric to vector bundles without a metric. Just forget about vector. Forget about functor. But you can do more complicated stuff. You can do map from GLN, say, to GLN squared, which is a tensor product of your matrix with itself. And this gives you the functor of taking vector space and take its tensor, so vector bundle and take its tensor with itself. And you can take all the Schur functors, you can also consider as a map from, they're all coming from some representations of GLN, so all can consider as a map from GLN to somewhere. So for example, you could take the determinant, and this is a map from GLN to GL1, and this gives you a functor from vector spaces to one-dimensional spaces, or from vector bundles to one-dimensional bundle. What you get when we start with vector bundle. So what is this functor? I lost it. So we have a map between GLN to GL1. Determinant. So this gives you a functor between the category of n-dimensional vector bundles to the category of one-dimensional vector bundles. To be honest, not the entire category, you only consider isomorphisms, but it doesn't, in this case, doesn't really matter. So what you will get, what is this functor?
Probably top differential form.
Exactly. And if you take instead of determinant absolute value of determinant, then it will be densities. And you can do everything for symmetric powers, etc. So there are lots of morphisms from one GLN to another GLN, and they all give you functors between bundles themselves, but with different dimensions. So the map should be continuous, like the functor should be continuous. Okay, so I think we can make a break, and after 10-minute break, we will do unit grammar. So you asked about non-continuous functors. So it's like non-continuous. So if you just consider not the category but the groupoid of vector spaces, so it's like non-continuous maps from vector spaces from GLN to say itself or to other GLN. Do you have non-continuous homomorphism from GLN to itself? Probably yes. Yes.
What's it in there? I'm sure.
I was not sure of it.
We have a theorem that every continuous group has a structure.
Yeah, but I don't non-continuous. Yes. Yeah, a continuous map will be an elite. But which is the non-continuous. Non-continuous probably totally different. So start with it. Yeah, okay, let's do from GLN C to GLN C, you have lots of automorphisms. But you want to be no, you don't want to be early. Just fun, so don't attempt to guide. So for GLN C, so let's do this. The problem is R does not have filter origin. Because we don't need filter or filter. Yes, from GL1 to GL1. At the most group, I'll have lots of automorphisms. So what's the
Non-continuous.
Yeah. What is R additive group? It's like R additive group times plus minus 1. As an additive group, we have lots of taking basis of R over C over Q and take any linear map. then take its log.
זה המשפט הכי ברור.
Yeah, so totally disaster.
Yeah, it's a little complicated. Yeah, it's okay, but
זה אמור להיות משהו חשוב.
no, we can. No, so what do you want from the resolution?
זה אמור להיות משהו כמו, כאילו, זה אמור לתת לך כלי עיכוב, אתה רוצה לחקור משהו, במקום לחקור את הדבר הזה, אתה חוקר משהו, קטגוריה אחרת שהיא נחמדת, או כזה, קצת כזה כמו, לפחות ממה שהבנתי, כן, זה היה בוויקיפדיה, שאם אתה רוצה לחקור באיזשהו רינג, אז אתה חוקר את המודול סופר והטרנד, כדי להגיד משהו על כזה.
What the emotions?
אבל ידעת שתי סורנה על זה. כן, אין שיש.
That's not for me.
Also, can we say that true functor, so that we could represent densities you follow true functor? So this map is not actually to vector spaces, but to a set of vector spaces. No, it's an representation.
What you doing here? So you have shoe factor lambda n.
Yeah, and we have that natural action of a set on this object. So it's not only vector space, but it's a representation of a set. So we can do this thing.
No, then you will get it back. So lambda n. Here you should put representation of a set. So this is standard representation.
Oh, yeah.
And then you
Right.
You see, the count of densities or the bundle of densities is only in real context. Can't think at the field. But you can consider the composition of the lambda n and then take the absolute value. So we have the function of absolute value from one-dimensional real vector spaces to one-dimensional real vector spaces. If you have one-dimensional real vector space, you can take the absolute value. So how you do it? Okay, one way to do it. So you should first do something weird. So you consider all the maps V star to R such that f of lambda v equal to lambda f.
זה וקטור בנדל?
Yes, so this is just so this functor mapping v to this is just identical. And now you put this the absolute value of the space with the same also one-dimensional space, but it's slightly different. You erase some of the information to things might becoming more applicable.
כאילו פון, מי שמציע פון.
מה ספציפי? ומה לנושא?
אבל די כאילו, הרבה מאוד מזה בא במכה.
למה? זה לא היה מי ששם את זה.
אני במכה.
אז כאילו זה כבר בזמן שבו כל הדברים כבר ידעו. זה מאוד כבר ברור שיש קשיים.
כן, נדע שהאקוויבלנט פקד בגובה זה ממש טוב, כאילו ממש ממש טוב. כאילו הפנימה זה מופיע, ה-Natural Transformation זה היה לא כזה. זה fully subjective essentially, כאילו fully,
וזה כן מספיק. אם אתה שם לב,
זה הכל, זה בדיוק מה שאתה רוצה.
אוקיי, כי זה הפול אפקט נותן לך את האסנס של אינג'קטיב, ואז פשוט לך את האסנס של הסושי. זה essentially by-injective.
כן.
זה מספיק. כן. לא, אבל כן, זה לא כיף, פשוט, אני לא מבין. אבל כמה כבר סבל זה, כי כאילו בשבוע ביידן לא היה כמעט שום דבר. נגיד, כן.
זה קצת נסה להסתכל על הקורס, אתה רוצה לי, אתה לא רוצה לקחת לשיעור בבית וכזה.
נכון. אף אחד יש הרבה מתרכזים על החומר נטו. בקשר ל... זה מאוד יכול להיות זה מה שכאילו בעיקרי פחד את הקורס בשביל ללמוד מלא דברים קטנים כל התקנים האחרים במתמטיקה. חושב שהמרצה יכול להגיד את זה באופן שפוי שהוא מצפה שאף אחד לא יודע אחוז. לא טעיתי, נמצא בשמונה דמו. אז... בסדר. טוב, פעם הבאה שלך, מה יהיה פה מובן? מה יהיה מובן?
בן אדם כזה שלא מבין שקורה. אני
אני
מכירה
לא
את זה
יודע.
כבר.
רק שתדע את העשר פעם, כאילו...
כן.
זה מצחיק. לא הייתי כותב הרצאות, פשוט הייתי שורק כל זה בראש, ואז קבלת האינסולין כזה, זה מגניב.
אז פשוט הייתי קולטת הכל.
הייתי קולט, שומר את זה, אני חושב על זה טיפה כהרצאה, זה אותה מספיק.
כן, זה ראש שלי גם. אז מה אתה עושה? לפחות יש הקלטה.
סתם, נגיד, הצעה קודמת, יש לנו קצת הגדרות, יש מישהו כמו שמעתי בפור הבית, אני חושב שזה בסדר. כולי שתי פה, עד לפי פה, זה נקרא לו. אני מסכים לזכור את זה צמוד. זה לא אמר. תמשיך הלאה. היה כשהוא פה במחים.
אפשר לשאול את זה.
ואז הוא השתנה אני. גם אז הוא השתנה. גם הוא יודע את עושה.
אז כשתמיד יש ביגר פיש, כי נגיד יש עכשיו הרבה פעמים
טוב עכשיו,
טופיקס,
לא משנה כמה
ואז
טוב,
כאילו בשביל זה.
לא משנה כמה טוב אתה, יהיה עשייתי או רוסי שטוב. מתמטיקה, או יהיה רוסי שטוב. אני מצקן. אני עושה.
באמת, או שאתה גם רוסי. אתה גם רוסי. אז אתה תדבר.
אני הבנתי. לא, אבל אתה, אפשר לומר שאתה פולני, בדרך. כן.
זה לא רע.
כן.
אז כאילו,
So we're ready to continue. Let me click. What?
oh, maybe someday, like, maybe someday we'll be happy to hear one more time the explanation for this.
Okay, something that I did want to say about this. Just maybe a simple example. Hopefully it will work. So we already discussed that BG, the category with having one object and morphisms are in G, is equivalent with the category of G principal spaces. And if G is GLN, the R, then this category is equivalent to the category of vector. Of vector spaces with dimension n over the field. To be honest, this is groupoid and this is not, so we need to take the corresponding groupoid. So the categories or morphisms are isomorphic. The subcategory of this category where we keep on its item. This is very easy to see that these two categories are equivalent. So we get also such a group. And this is a special case of this when we're talking about one point. So vectors bundles of our points are vector spaces, and they're the same like GLN principles. We don't know if it's X, but yeah, I can ask Rahul to discuss this. So, Gauss lemma, some would say it's the most important lemma in category theory. Probably, but certainly one of the most important statements, these basic statements. And like intuitively what it says that you can reconstruct all the information on an object, knowing morphisms from this object or morphisms to this object. this kind of give you a posteriori justification for category theory, why it's okay to forget all the internal structure and only think about morphisms, because you can reconstruct everything from morphism. Of course, it's not really true. You can reconstruct everything in the framework of category theory, so you kind of have to trust category theory in order justification makes sense. So it's slightly justification, but still give you something. So, and what this category, what the Newton lemma says. So we have a category C, and we have a category of functors from C to Z, of contravariant functors from C to Z, so functor from C up to Z. And we have here a functor, I don't know, let's denote by like C, the unit functor. Let's define it. As usual, when you have an object, because we're lazy, IC of an object X. So this should be a functor here of an object Y. Should define a functor here, so we need to say what its value on some object. Again, I'm lazy and only define the objects. If more, so let me see if I remember that direction correctly. Pretty sure it's from Y with. Of course, you can do it the other way around, but this kind of the standard way, that is the opposite way. So in this way, here you get contravariant functors, but this functor is covariant. If you do it the other way around, then it will be opposite. But instead of doing the other way around, the easiest thing is just to do it to both opposite categories. So it's enough to do it once. Good. It's called the lemma, but it's kind of important, so let's call it theorem. Anyway, IC is what we. So you remember what does it mean for functor to be fully faithful? So the definition is that it's isomorphism at the level of Holmes, of Morse. But the intuition is that this functor is equivalent to its image or to its essential image. So to anything here, they're isomorphic to something in the image. So let's call it essential image and by some name. Right? This category is sometimes also called reshifts. I did define what are shifts, but in different contexts. So let's start with reshifts. And this category we called, so the essential image of R is called the category of representable functors or representable by shifts. So we denote it by rep E of. So essential image again is all the objects here that are isomorphic to an object that comes from C. So such an object is called representable functor. So it's a functor, a contravariant functor from C to Z. And there is and the lemma tells you that there is an equivalence category between the category between C and the category of representable functors. So equivalence of categories, but it is only like one-way equivalence. You have functor which is fully faithful and essentially surjective. You have a functor to the other direction, but it depends on choices. So sometimes we can fix a choice from here to C, like choosing the representation of a factor.
So it means that every P we can remove by shift of sets, some shift of sets with saving all information about morphisms.
Can you repeat from the beginning?
I mean, if we have, for example, some scheme where we can construct many shifts on it, and
So the name per sheaf is a bit confusing, I think, at this point. The sheaves are not on a given object. They are sheaves on the entire category, which is something like didn't define. But yes, if you have a scheme or object in a category, but start with a scheme, you can reconstruct all the information in the scheme by knowing what are morphisms from another scheme to this scheme. In fact, you even don't need to range over all the other schemes. But when I say knowing, you need to know this not only as the corresponding that give you this set, but also for if you have scheme X, you want to know what it is. You can consider all for any S to ask what are the morphisms from S to X. But it's not enough just to know it as a list of sets. You also, when you have a map from S to T and morphism from T to X, you have morphism from S to X.
No, but I mean that for any shift on scheme, we can think about it like a shift
Shift on S scheme or shift on the category of schemes?
on scheme, I think.
On S scheme.
Yeah.
Okay.
We can think about it just
Look,
as a
it's
shift.
not related to the state. Maybe it's called, but it's not related.
Okay.
Because we did not. Maybe it's related in the sense that it's built over it, but more advanced, but this kind not. So maybe we should do it after the class. But okay, so we don't need to talk about schemes, which we probably some of you don't know what are. But you can take any category that you like, say topological spaces. You want to describe topological space. You don't need to actually describe who are its points and what are its open sets. You can just say, given another topological set space, I want to know what are morphism from the other topological set to my set, the space to my space. And if I know this list, huge list of sets for all, so I want topological space X, for any S, I know what is the collection of all continuous map. I have this collection, but not only as a just stupid list, but also given a map from S to T. We have map from one set, from this set to this set. And when I have this data, I can uniquely reconstruct my topological space. And so this is a very powerful machine.
Uniquely up to isomorphism.
Uniquely up to isomorphism, but it's more than just that, because you can reconstruct it as an object in the category. So you can actually, you have to choose something, but you can actually produce an object in the category, and then for any, and it will be functorial. So if you have all this data and another set of data like this, and morphism between the two sets of data, in other words, morphism here, it will give you a morphism from one continuous space to another. And so it's not just on the level of isomorphism classes, but it's actually occurrences of categories. So what does it mean? It means that any construction that you want to perform with objects in the category, you can perform with functors instead. Okay, you can say, okay, functors are more complicated, but not really, because there are functors to sets. So you can perform some construction on the level of sets. Some functor from sets to themselves. So each time you have a functor from sets to sets, you can try to make this functor from any category to itself. So all the construction that we had before, whether it was a initial object, terminal, no, in fact, half of them. Terminal objects, limit, but okay, the other half you can do with opposite category. And coproduct, product, etc. You can just perform on sets and then try to perform them on functors. So let me explain what we do. So for example, I want to define the product. So I already defined the product, now I want to redefine the notion of product. I have two products, X and Y, you see. So I have two functors, IC of X and IC of Y. Now I can define IC of X times IC of Y. How do I define it? this thing for an object A, maybe I see X A times I see X of Y, sorry. And so I know what is product of sets, so I can define product of product of functors with values in sets, just like acting like the way. Now I get a new functor. Maybe it's representable, maybe not. If it is representable, it's representable by some object. So I will define the object that represents it to be the. So if it's representable, there is a unique isomorphism and object that represent it. But in fact, I just can once and for all choose a representation functor, I don't know how to call it, R. And I can just apply, so I can define X times Y as a representation functor. I don't know, like a graphical. Apply to the X. So it might not work because this might be not representable. But if it is representable, then it's well-defined object. And as you remember, product is not necessarily defined, but it's always defined as a functor. So you always have an object here, a ratio for a functor here, and which is a product of your two objects. It might be a functor and might be not. It might be representable, might be not. So you can ask the same for any limit. So you have a limit of some diagram of objects. You apply the Leonardo functor to this diagram. You get diagram of functors. And you can take the limit of the diagram. So here, this category have all limits because it just applies the limits on the sets. Am I right about limits? I'm pretty sure, yes. So you apply the limit on the values, so you get new functor, and this functor might be representable, might not be representable. If it is representable, the guy that represents it is a limit. I mean, if not, it means that the limit does not exist. So you can say that all the construction in category theory works through Unedel. It's not too much informative statement because you can also say that all the construction in category theory works through the notion of terminal object because everything is a terminal object in some category. Or everything is a limit and everything is representing object for a factor. So each one of them can be a formula here expressed using the other, so it doesn't really mean that one of them is better than the others, but somehow the Leonardo functor is really feels more powerful. For example, the open form of topology that we discussed before. So we want to define internal home, internal morph from two topological spaces. Okay, maybe I don't know what it is in general. I don't want to discuss what a compact set, open set. But I do know what is product of two topological spaces. This is easy. So now I have a space Z, and I ask what are morphisms from Z to this morph. Okay, it's kind of easy. Yes, you have point in Z. For any point in Z, you need to define in a continuous way, of course, the map from X to Y. So for any point in Z and point in X, you need to define point in Y, and it should be continuous. So you can define it to be morph of X times Y to Z. So this is so this is well defined in at least topological spaces, and now you don't really know what it is. Yes, this is a question mark, but you know what a morphism is. In other words, you construct a functor from top, quantavariant functor from top to sets. So theorem, I think it's theorem. Maybe it's true in some generalities of topological spaces, but for reasonable topological spaces, this function is representable, and it's representable by topological space, which is the collection of all continuous functions, continuous mappings from X to Y with the open compact topology. I'm pretty sure this will get a chain. I'm pretty sure this is what you get in a reasonable general.
Even this function must be continuous maps from z times f to the y, but not to the.
Oh, sorry. Z times X to Y. And by the way, you can try to do it in any category. It will not always will give you the notion of internal home that you use to this category, but you can always find it. It's not always representable, and even if it is representable, it's not always like in vector spaces. You will kind of get the wrong answer because you know that in vector spaces, what are maps from vector space Z say to more linear maps from X to Y. And just a bilinear map, yes. A bilinear map is represented by here we need to take the tensor point, not the point. So it's you can try to do it always, but it doesn't always work in the way you expect it to work. But it makes sense of. Okay, let's try to prove the unit lemma. How do we prove? So, as usual in category theory, most of the things are rather trivial, but sometimes very cumbersome. So there are lots of steps that you need to unwind, and then you see that nothing sticks.
And think about anything in mathematics.
Not in the same way. Yes, of course, then you. No, but often you don't really know what to do in the next step. You go like feel stuck. And in category theory, don't really feel stuck usually. There are lots of steps, but each step is rather little. Yes, once you wrote everything down. Sometimes you need some external construction. But the formulation of another lemma itself is kind of, it's not obvious construction of why to do it. Yeah. But at this point, I do not presume that a trick to prove some theorem and just say it's part of the material, because the proof is kind of straightforward. Okay. So we'll start with faithfulness and then put the fully faithfulness. We need some notations first. So we have X, where Y, we have 2 modes of X, Y, and we want to show that if the unit image is different, then they are different. So let's see what is a unit image. I see X, I call it a function that sends Y to 4 Y. No, not Y is Z. So now we need to catch some Z to use it in order to see, okay, if so we have ICX and we have IC. Y.
Shouldn't it be more of ZX?
Oh, yeah, actually. Yeah. Sorry. So, okay, maybe that is IC. Y and IC. I, and we know that these two guys are different. We want to prove that these two guys are different. So what is these two guys? These two guys are meshes between functors. So IC P is Z is a map here. So there's a lot of information. For any z, we have a map like this, and we know. Sorry, we want to show that if these are different, then these are different. So, or the opposite, we know that these are the same for any z, and we want to show that these are the same. So for any z, it's too much information, it's hard to use, so we need to pick some z, and that will give us lots of knowledge. So do you have some suggestions? What z to take?
We want to different two morphisms. We can use any monomorphism. The excellent monomorphism is an identity.
What to? Exactly. So, so who should be z? But maybe here I was wrong. Well, it's a contravariant function, so it goes like this. Where you map from x to y. No, sorry, confused. No, we have a map from x to y, and we map from z to x. No, because the unit function is covariant. So, who should we take to be z? So we don't have too many options. So the category is huge and there are lots of objects there, but we don't know their names. We can't assume anything. We can't take the initial object or terminal object because maybe they not exist. So basically there are only two objects which are exist. So what are these two objects?
X and Y.
X and Y. So two objects which we know for certain that they are set. And okay, so we can try both of them and see what fits better. So I'm pretty sure that X fits better. Let's see if it's, no, I didn't open it down, so let's go with X. So we have more XX, and then we have ICT of Z, sorry, X, more X. We have ICC and ICC, and we know that they're the same, and we hope to just use this tiny piece of information to get that phi and psi are the same. But still, it's a lot of information. Two maps are the same. What does it mean that two maps are the same? It means that for any element here, we'll get the same element here. No, with respect to both maps. And here again, lots of maps, too much information. We can't use such lots of information. For one hand, on the other hand, we don't know anything about the category. So in fact, we don't even know that there are many maps here. But still, so we can try to use the restrictive part of the information, just one map. What one map we know for sure that we have here? What? Identity map. And now this map maps somewhere here under the unit functor. So I didn't define the unit functor on the functor, I only defined it on sets. But we can just now see the definition. But before the definition, do you have a guess where this the map maps to here?
Maybe 5.
We don't have too much options here. Yes, more XY might be huge, but all we know is have just two morphisms for phi and psi, but psi have nothing to do with this picture. We only discuss phi. So the statement is that the unit functor applies to phi maps the identity map on X to the map phi from X to Y. And the same, unit functor applies to psi maps the identity map on X to the map psi. So phi is equal to identity to unit C applied to phi applied to identity X. And if you write psi here, we get psi here. So if these two guys are the same, then phi and psi have to be the same. We would like to see whether we can just prove it. Why? So what is your neda functor actually do? What is your neda? Phi applied to alpha. When alpha alpha is of Z. Okay, we didn't define, so we have to define now, and again, we do the only reasonable thing that we can do. And so we need to get a morphism from Z to Y, and we have morphism from X to Y, so twice. First apply alpha, and then alpha. So this is the definition of what you let the functor do on specific morphisms. And of course, identity composed with phi is phi, and C is 4-based tautology. And so we prove the faithfulness part. Any suggestion how to prove the fully faithfulness part? So we did more than prove the faithfulness part, yes. We, knowing IC of phi, written a formula for phi. Yes, so it's already gives a good start for proving the full faithfulness part. So what does it mean full faithfulness part? We have a morphism between IC of X and IC of Y, and we want to find a morphism between X and Y that corresponds to this morphism. So in mathematics, when you want to show that something is onto, or we want to find something, there are usually two stages. First of all, you need to actually find something, construct something, and then to check that this something do the job. And usually the first is harder than the second, because the first you have to kind of invent something, and the second is kind of computation. Often it's not the case, but I see. In the first approximation, the second step is the easy step. And here we already did basically the first step, because we find, so knowing IC of phi, we could reconstruct phi. So given a morphism between two, and between IC of X and IC of Y, we can reconstruct phi. Maybe this reconstruction will be wrong, but we know what to do. So this is what we need to do, to plug in identity X. So let's say. So you have IC of X, IC Y. You have alpha here. I want to find phi from X to Y such that alpha is equal to IC of phi. So how will we define phi? Equal to, I take alpha. Alpha is a morphism between two functors. So it means that for any object, you get a morphism between the values of the functors on this object. So what object will you plug in? We would plug in X. So if alpha is a morphism like this, and alpha of X is a morphism of an IC of X to IC of Y. So now I plug identity X, and yet, and this is the element in morphism. See when we can press absolute options. Support the option. IC of X is morphism from IC of X of IC of Y of X is morphism from X to Y. But now, of course, you need to show that IC of Y is equal to I. And this you need to show for any other object. So I think at that point I will leave it as an exercise. well, maybe not. Let's finish out with this though. Let me try to do it. I hope we're not confused too much. So what we need to do? Where's Z? But maybe before I start, do you have any questions up to now? Do you follow the line now? You want me to repeat? You don't want me to repeat? You want me to continue to do this? Or you prefer to do it home? Or you abstain?
No, continue.
Uh, and the rest abstain.
You can continue, write it all down, put it down.
So what we need to show is that IC of phi equal to alpha. So IC of phi of z. What does it mean? This is a map for more of IC of z. IC phi is a map for x to so IC of phi is a map from IC of x of to IC of y. To show that this map is equal to alpha, we need to show it for any z. So IC of x of z, so IC of y. So this is IC of phi. What is this? This is IC of phi of this. What is this? This is more from z to x, and this is more from y to from z to y. And how it is defined? So if we have no beta here, so beta maps to first perform beta and then perform phi. So who is phi? Phi is alpha of identity. Alpha x of identity. So we want to show that this is alpha. Okay, so how do we show it? Well, confusing. This is your question. Alpha of zero, of course. So what do we know about alpha? Alpha is morphism of functor. Okay. So let's use it. I C of x of z, I C of y of z, R C of x, I y. And now I want to choose a morphism between x and z. How will I choose morphism between and we have beta and morphism between z. So here we will have IC of x of beta. And here, no. Here we need to remember that something is contravariant. IC is contravariant. So here we have IC of x. Not IC of x, not a functor, it's a contravariant functor. So here we have map like this. And here, what do we have? A map. The map coming from alpha. It's alpha. Alpha is here. Alpha of x. And here what do we have? A map coming. So it's IC Y of beta. And what do we have here? Alpha of Z. So the fact that we are morphing of functors, and that alpha is morphing of functors, means that this diagonal is commutative. Now let's take identity here. Ask where it goes here. So identity here will go to phi here. Yes? And then ask where it goes here. So it goes to phi composed with beta. Now we can ask where it goes here. Identity here goes to beta. And where it goes here? It goes to alpha z of beta. This alpha z, beta, beta. So since this diagram is commutative, these two guys should be equal. This is equal alpha of beta, which is exactly what we that IC of phi is equal to alpha. IC of phi of beta. This is I. Maybe it was confusing, probably better to do it from scratch at home, but if you start, then you can look at the internet or look at your notes here or at the video. The idea is that you should not be stuck. So basically in each step you have more or less one option. Sometimes you have two options, like choosing between X and Y. And maybe one trick that you need to remember that any object has an identity map, and if you don't know what to choose, you choose this. And okay, so this was kind of straightforward. The real immediate problem of the United Cinema, which I think if you try anyone started to do it directly, and it was not as straightforward. So if you have IC of X, which is isomorphic, somehow isomorphic IC Y, and then IC of then X is isomorphic. Yeah. Because face the functors maps is injection on the level of isomorphism classes. And okay, this composition of two statements, one is obvious and the other is not obvious but straightforward. But by itself it's already kind of less obvious, and if you just start to say, okay, I want to shortcut, I just want this, I don't want the entire lemma. Not really. It will not be easier, it will be harder than the entire United. So, for example, in algebraic topology, one application of this thing is that if you have two CW complexes, X and Y, and for any CW complex, so do you know what is CW complex? So for any CW complex Z, we know that, say, this category that we didn't discuss, the homotopical category of topological spaces, the category of objects are topological spaces, and maps are continuous maps up to homotopy. So you know that continuous map up to homotopy from like Z to X are the same. Like, oh, okay, so you need to be here more accurate. Because either you say that you have isomorphism functors, which is kind of complicated, or you have concrete map from X to Y, X to Y, and then you have a map from here to here. So, right? So if you know that this map is bijection, then you deduce the original map was a homotopy equivalent. which kind of looks weird, yes, because how would you find the map to the other direction? So in fact, you know how to find the next to the other direction. You put here either y or z. Probably you put here y, and so here you take identity and you have what you get here. But still, it's kind of rather powerful statement, and you can make it even more powerful with the White theorem. So how you check that this thing is bijection for any set? You kind of need to walk over all CW complexes and check for them. But you can make a discount. You can check it only for spheres. Once you know that there is a map from X to Y, and it induces bijection for all spheres, then it is homotopy equivalence. It's not a real thing, but this proof have two steps. First of all, you show that if it's induced bijection of spheres, then everything is pointed, of course. Then it induces bijection of for any CW complex, which is not trivial but kind of straightforward. No, not really straightforward. And then from this you get homotopy equivalence from X to Y if X and Y are CW complexes, kind of completely for free from the Netherlands, which is very general, kind of by definition easier than anything we do in something concrete like algebraic topology. And for spheres, these are just the homotopy groups. So the White theorem says that if you have a map between CW complexes that induces bijection or isomorphism on the homotopy group, then it is homotopic equivalence. So if there are, for general topological spaces, it's not true. So this weak homotopic equivalence, which by definition basically means that this is bijection. Together with Horowitz theorem, so when you study homologies, you probably or maybe you already studied this, and then basically if a map induces isomorphism on the fundamental group and on all homology groups, then it is homotopic. So it kind of gives you the wrong impression that in order to, so all algebraic topology is encoded in these two objects, homotopy group and higher homology groups. And this is of course wrong because you need actually, or maybe it is correct when you consider it as a functor, so you need actually to have a map from X to Y in order to reconstruct X from its homology, in order to show that they are homotopic equivalent. So if you just have sequence of groups here and sequence of group here and they are absolutely isomorphic, it's not. There are two very different spaces that have the same fundamental group and same homology groups. This is misleading impression, but very useful. 10 minutes, 15-minute break, and then I join functors. I don't touch it first.
Put it definition כן. אוקיי. אז קודם זה כאילו תחשוב הכל זה יותר אינטואיטיבי. כן. אוקיי. basically כאילו נגיד יש לך שתי אובייקטים, ואתה יודע שאם תיקח כאילו אותו אובייקט שלישי, תיקח את הסט של כל המורפיזם מהאובייקט הזה לראשון והאובייקט הזה לשני. אז אם הם תמיד כאילו איזומורפים אחד שני, יש לה קבוצות לב תמיד מדברות מסתכלים, אז זה שאקסם מדבר. אז זה כאילו, אתה יכול לעשות determine עם x ו-y אותו דבר, אבל כאילו, אתה מסתכל על כל כל אובייקט אחר. זה
זה קור גבי.
כן, לא. זה שקול, כפולי פייפו שקול דדם. יש לך פולי פייפו, זה פשוט אותו דבר כמו essentially injected. זה כן. כן, למה יש לו, לוקח אובייקט X, הופך אותו לפונקציה שהוא לוקח אובייקט אחר, הוא פשוט אומר לך, אוקיי, זה מה עם פולומורפיזם עם אובייקט Y ל-X, אבל אתה גם הופך לסקל האנקר שממנו כאילו פולומורפיזמים בנים, אתה בודק כל אחד מפולומורפיזמים שלי, עם שתי פונקטורים איזומורפיים, זה בייסיקלי מה שזה אומר, כאילו בפרקטיס, זה שתיקח אותו אובייקט, תיקח את ה-Z, תיקח את המורפיזם של X, תיקח את המורפיזם של Y, איכשהו יצא לך אותו סט. ואם זה נכון לכל Z, אז זה ש-X and Y נגדרו באיזומורפיים. That's it.
כן, טוב. כאילו, למי אתה אומר?
חכם, אני לא הבנתי מן הסתם.
רק אותך פה מודל מאוד חלקית, כאילו יודעת פה רק איך האובייקטים מורכבים, כאילו צריך לתת גם את הפקטור וגם כאילו אתה צריך לתת גם את המורפיזם וגם את האובייקטים בשתי הרמות. נכון?
כן, אבל הוא לא יגע את המורפיזמים.
כן, הוא משתמש בהם.
נכון, משתמש. שאפשר לנחש.
אני חושב שאמרת את זה, אבל זה כאילו בוודאות לכם לא יודעים. כאילו, צריך לתת פליקס.
כן. שזה שנייה. פשוט הפקטור הזה. צריך לקחת כיף מורפיזם בין X ו-Y ולהפוך אותו למורפיזם בין פקטורים, שזה פשוט natural transformation. אז בעצם
אני לא מצליח לחשוב עליו, כאילו, אתה צודק, זה natural transformation, אבל אני לא מצליח לחשוב עליו פה שצריך.
כן, צריך לכתוב את זה ממש.
כן, אז כאילו, זה ברור, זה כנראה זה מאוד אינטואיטיבי, כן, יש לה כיפות אחת, אבל לא.
אבל צריך קצת דיאגרמה.
ואתה אומר, אם אלגוריתם כאילו איזומורפי, זה אומר שעבור כל... זה רק אומר ש-natural transformation ביניהם הוא natural איזומורפי, אבל איך זה קשור לזדים של...
אז אם אתה נראה לי משחק עם actual דיאגרמה, בסוף אתה מבין שזה בייסקי שקול לזה של כל Z, המורפיזם מ-Z ל-X, זה אותו דבר כמו המורפיזם מ-Z ל-Y. זה אם אתה אשכרה מסתכל על הדיאגרמה ופותח את ה-definition, אתה עושים תראה את זה. כי זה מה ששמתי לב כשעשיתי את שאלה 3. כאילו בשאלה 3 אתה גם צריך כאילו להוכיח שיש לך פקטור בין קטגוריה לקטגוריה של פקטורים, הוא equivalence. אז שם הסתכלתי על הגדול וראיתי אוקיי, אז זה כאילו העובדה שיש natural transformation איזומורפית, זה כאילו יוצר איזשהו כאילו שישב בין האובייקטים. כאילו זה תוקע, אז נראה לי זה בערך מה שזה יצא. אם אתה אשכרה תכתוב את הדיאגרמה. שאפשר לנסות.
עזוב, אני אעשה את זה, אני...
באמת?
כן, אני קצת קוק.
דקוקט?
כן. כשאתה אמרת את זה יחסית, אתה ראית את זה די ישר עם הקורולר. זה לא בדרך ראית את זה כל כך ישר. נכון.
כן. כן, שפולי פייפו זה אומר, זה מה שהוא אמר גם על זה קודם, זה ממש פשוט, רק צריך להוכיח.
נכון, אבל מה זה בעצם אומר?
זה essentially injected.
לא, נכון, אבל למה... כאילו, איך מפה הבנת את הקטע שתיקח כל Z, ואם הם... יש להם את אותו סט של...
כי עוד פעם, אני פותח את ההגדרה של מה זה אומר ששתי פונקטורים איזומורפיים. אם אתה פותח את ההגדרה, אתה הולך לראות שזה, יש לך, אתה תוקע, יש שם condition per object. כי הרי זה כאילו, מורפיזם בין שתי פונקטורים זה כאילו משפחה של מורפיזם בין שתי אובייקטים. בין אובייקט לעצמו. נו כאילו f של x l g של x. זה המשפחה. יש לך one מורפיזם כזה.
כן, במקרה הזה זה מ-i של x ל-x ל-i של y של...
לא, זה I
של X
זה I של X של
A
A ל-I של X לא, אתה צודק. זה I של X של A ל-I של Y של
B.
A.
לא.
זה כן, זה A ואז פה ה-B's.
כן, אז B זה ככה.
כן, כן. אז נראה לי זה תוקע לך משהו מעניין. שאתה צריך לשחק את המפות פה וזה צריך להיות קומיות ככה. אז זה כאילו, זה יעשה לי סטריפט ככה בשום אופן. על ה-A ו-B.
כאילו, כאן שכונת אז בהתחלה זה היה נראה לי קרוא לבי נכון, אבל באמת זה עצוב.
שאלה פשוט על אינטואיציה. האם הדמה של יונדר אומרת לנו שאם יש לנו שתי אובייקטים בקטגוריה X ו-Y, ואם ניקח אובייקט שלישי Z, אז אם תמיד לכל Z כזה המורפיזם מ-Z ל-X והמורפיזם מ-Z ל-Y גם אותה קבוצה, אז זה אומר ש-X ו-Y הם איזומורפיים?
נכון, אבל לא בדיוק ככה, כן? כי מה זה אומר אותה קבוצה? שוויון בקבוצות, זה אין לנו הרבה מה לעשות. רוצים להתקה בין הקבוצות האלה, ושתהיה ביאקציה, ושכל מיני דיאגרמות של קומפטיביות, שניתן להתקה מ-Z ל-Z פריים, דיאגרמות שתקבל קומפטיביות. ואז
לעזור שתי שניות מה זה אומר רפרזנטבל פונקטור.
זה פונקטור, בוא נדבר על הקטגוריה הזאת, שמגיע מאובייקט בסיס, זאת אומרת שאיזומורפי למשהו שבא מאובייקט בסיס.
שהוא איזומורפי להום, שזה פונקטור שמגיד להום משהו להום.
בדיוק. כל רפרזנטבל פונקטור בעיקרון מתאים לו אובייקט שמייצג אותו, לא באמת יחיד, אבל אפשר לבנות פונקטור שמשחזר את האובייקט. יהיה תלוי בבחירות, אבל אפשר לבחור אותו אחת ולתמיד.
אז לפי ההגדרה הזאת של כול C.
כן, הקטגוריה של כל הרפרזנטבל פונקטור שקולה ל-C. לכן, כל דבר שעושה בתורת קטגוריות, אתה יכול להגיד, אני בכלל לא עובד עם אובייקטים, אני עובד עם רפרזנטבל פונקטורס, אני עובד עם פונקטורים, והם מתפלל שימצאו רפרזנטבל.
אתה כאילו הגדרת פרודקט של שתי פונקטורים מבלי שאם הוא פרזנטבל אז קיים גם פרודקט בקטגוריה, שתי אובייקטים.
ואם לא, אז אני נשאר רק עם פונקטור שלא רפרזנטבל. וגם הרבה פעמים, ככשו אתה לא מרוצה מהתוצאה, זאת אומרת, הרבה פעמים אתה רואה שיש כל מיני דברים שאתה רוצה לבנות, והם לא רפרזנטבל, אבל אתה רוצה שיהיו רפרזנטבל, אז אתה מגדיר מחדש את הקטגוריה שלך. להכיל חלק, אתה בדרך כלל לא רוצה להתפרע, לא רוצה להוסיף את הכל, אבל אתה יכול להוסיף חלק. אולי עכשיו אני אגיד על זה משהו כמה דקות. כל פעם אני בא עם עותק חדש של הנושאים של ההרצאות, ואז כאן מצטברים לאט לאט, אני תמיד שוכח. זה פיירפוקס. Okay, so we can start? לא רוצה, אני לא רוצה. What should I write now? Is this one? So the recollection, so we have the inner functor from C to large epsilon C. So this functor reserves limits. To start with n diagonal here, you can take its limit here or take its limit here, you get the same. And this category have all limits, and this is a way to can be a way to define or to construct limits in C. So you take diagonal here, send it here, takes a limit, and hope that it's coming from an object here. If that's you're happy, if not, means that C don't have this limit. So now this category also have co-limits, although we like kind of better build to limits in C, but it also has co-limits. But this functor does not preserve co-limits. You cannot use the unit functor in order to construct co-limits. You can do it, but then you have to work with the opposite word. Just work the opposite category and do everything there. But if you fix the x direction, then the embedding does not preserve co-limits. This does preserve. This has all co-limits, but if you take the item here, take it here, take its co-limit, maybe it will be representable, maybe not, but it will have nothing to do with the limit in the original diagram. Moreover, in some sense, I will not discuss it exactly. You can consider this category as a category generated by all add artificially to see all the co-limits. But maybe this is a misleading way to state it. You don't really add all the co-limits, you recreate all co-limits in C because you change them, because you kind of do it freely, so you get things which are not the same as co-limits in C. But sometimes it does make sense to think about it like this. So we say that inside this category you have the image of C, the essential image of C, which are the representable functors, but sometimes you want to make it larger. So maybe the most important example is the example of schemes or algebraic varieties. You start to define what are algebraic varieties, and you usually start to define what are affine algebraic varieties. And from the beginning, you kind of see that you're not really happy with the results because you have very nice affine algebraic varieties, but you also want to glue them together to get something more complicated. Yeah, so you have the affine line, they're nice, but you also want to talk about the projective line. So projective lines, you know what is a projective line? You were the only one that said that you don't know what a algebraic variety is. But what is a projective line, you know?
Not sure.
Projective line is a collection of all lines in the plane. So lines from zero. And so it's basically almost the same as taking just one line which is not passing through zero, and then it's kind of parameterized for you all the lines, all but one. So it also has infinity. So you can, but the choice of infinity is arbitrary. You can take another line, and then it also will have all but one, but this time it's a different one. So it's something that basically almost looks like the affine line, and each locally looks like an affine line, and each time you can just choose different affine lines. So you have cover with, say, two affine lines together, cover the projective line. But each one of them is not a vector, not an affine algebraic variety. You cannot describe it with equations. So I draw it like a circle, but it's not an actual circle, yes. So what you do, you say, okay, algebraic variety is something that locally looks like affine algebraic variety. But what does it even mean? You need to put some framework where you can locally glue things. So if you read Kempf, then the way to do it is and you consider the category of topological spaces with a sheaf of functions. And if you read Grothendieck or Hartshorne, the way to do it, you take the topological spaces with, like we talk about schemes, and algebraic variety can be a special case. So topological spaces with a sheaf of rings. And yeah, you can do it this way, and this is still today probably the most standard way to do it. But it's look a bit artificial, so why we have to talk about these topological spaces? You start with some very specific category of affine algebraic varieties you want to extend. And then there is a more modern way to do it, which somehow still today is not very common for algebraic varieties because it kind of already was defined before this modern way, so why we'll define it. But for other objects like algebraic spaces or stacks, which are more general than algebraic varieties schemes, then it is a standard way. You just walk in press shifts over the category of algebraic varieties. So it looked very abstract, but at the end, what for you is algebraic variety? It's some of a fine algebraic variety. So what is a fine algebraic variety? A fine algebraic variety is something that is defined by a system of polynomial equations. So you can ask what is the set of the solution of this polynomial equation. And it's kind of the set of the solution is carry less information because you just forget about the geometric structure, just a set. But if you ask this question over any ring, say, not ring with one, then you basically have all the information. If you have a protocol that for any ring could say what is the set of the solution, and in a functorial way, so given a map between two rings, you have a map between the set of solutions, then you can completely reconstruct your fine algebraic variety. Why? Because the category of rings, or unital, or unital mutative rings. So if you work in schemes, so this category is just equivalent to the opposite category of the category of algebraic variety. So there are all sorts of schemes, of affine schemes. And if you want to work with variety, so you need to add here, restrict it a little bit, so finitely generated without equal. Never mind. So in this category, so functors from this category to sets. In this time I say just usual functor, not quantum functor, because this is already the opposite category of fine algebraic varieties. These are just press shifts on fine algebraic varieties. So finite varieties, you have the unit embedding T, and this is a fully faithful functor. So fine variety can be reconstructed as a functor like this. And then the only thing you need to say is okay, I want to define non-affine varieties. There also will be some objects here. Just not all the objects here. There are way too many objects here, but some reasonable objects that I like more than the others. Those who locally looks like a fine variety. So what does it really mean? So it's a little bit work to prove, but to formulate. But on the intuitive level, what is this gluing? Gluing is colimit, yes. Colimit with respect to some very specific embedding. We don't do general gluing. You don't glue over closed subsets, for example. You can do it, but you don't do it. When you define a fine variety, you glue over the risky open subsets. So you add some of the colimits, but not all of them. And this is something that just adds freely all of the colimits. But this is something really too large, for example, because it's change the colimits here. And when you work with the fine varieties, then you will change some of the colimits, but only those that you didn't like before. Yes. So fine varieties, you can have colimits which you don't like. For example, you still can try to glue two fine lines in order to get projective lines. So how do you do it? You have A1, you have A1, and you have A1 without 0. So this is a fine line, this is a fine line. Here you have the standard embedding of A1 without 0 to here. And here you have the inversion. So you have two copies of the fine line, and you glue everything but 0 to everything but 0, but after inverting. So it means that the 0 here will be infinity in what you got. And this looks like something, so you can consider the push out. And the push out in the category of algebraic varieties will be P1. So you see P1 have a fine line inside it, have another fine line inside it, but most of them is the same. So everything which is not the, so here, if you take this as your main line in P1, then the infinity is this line. But in the other line, this is 0. So everything which is not 0 in this line corresponds to something finite here, and everything which is not 0 in this line corresponds to something finite here. So you can glue and glue both of them with respect to this G1 and GM or affine line without zero, and we get P1. So this is a push-out diagram. Don't remember how to more push-out diagram. It's like this, and but only in the category of affine of algebraic varieties. In the category of affine algebraic varieties, this diagram does not exist. But surprisingly, these push-out do exist. It just, I think, do exist. It just will be 1 point. We like kind of just mesh everything to 1 point, which is kind of sad. Yes. Yeah. So some push-outs you don't really want to preserve. So you add push-outs, you don't want to do it in a completely free, crazy way, because you basically want to preserve the push-outs that make sense, but you don't want to preserve all of them. And the formal way to do it, you say, you consider this category, and you say that algebraic variety is an object here that satisfies some axioms, which basically make it a push-out of affine algebraic varieties along nice diagrams. You add some of it. Okay. Any questions before we go into adjoint functors? No questions.
So you said that general algebraic variety is a result of
Oh yeah, I'm losing electricity.
specific categories in the category. So,
Some specific co-limit of affine algebraic varieties, but in this category, not in this category, because sometimes here the co-limit will exist, but it will be bad. Almost there. This is code count, and there is some. Okay, so everything. So what can I erase? That one. So what are joint functors? So with some general procedure, you have a functor between one category and another category. You can construct functor to the other direction. And like in fact, you saw some similar procedure during linear algebra. If you have vector space with scalar product, and Hilbert space, whatever. and you have two vector spaces על map, למה תשלו עובד? זה כן יעבוד? זה גם גרוע. Then you can construct a map to the other direction, but somehow you need to use this additional structure of like the transpose map or the dual map, but you need to use the additional structure of the scalar product. Otherwise, you will get a map from the dual space to the dual space, and then you just use identification between the space and the dual map space using the scalar product. But somehow the bonus that you have in category theory that you always have a built-in scalar product from the category to itself. So you can have pairing, having two objects in category and get not really a number, but this time a set, which is just a home between them. It's not commutative, but it's something. And this gives you like a first attempt to define an adjoint function. So definition one, and given f of e, we say that G from E to, it's from D to C, adjoint. Sure. And if, so now what I want to write, I want to write it more. So the way you do it in linear algebra. So if x y, I want to write equal, but it's illegal, so we have to change it. More from x to g of y. Yeah, so you probably saw this formula in linear algebra when you take the pairing and then you change a to a star. But of course, this is illegal. So my next attempt will be to write isomorphic. Just knowing that there are isomorphic is not enough. So I want to have a morphism phi. And now this phi can depends both on x and on y. So you can consider this as I can fix y and let a x range, and then I get here objects which depends on a set which depends on x, and it depends in a factorial way. Because f is a functor and more is a functor, more to y is a functor. So this is so this is a functor. So what I actually want, I want this phi to be phi of say x, a fixed y, and then phi will be a map between the functor, like just note by definition, y maps, sorry, x maps to this, to the functor x maps to this. So it's a little bit complicated, and it is kind of a Borg symmetry fixed to y. So I can of course do the same for fixing x, and I can ask it even better to be morphism. So I can define the notion of functors of two variables, or say of product of two categories. So categories as objects are pair object here and object here, and then we have a functor from this product of c times d to sets. For each of these sides is a functor from c times d to sets. And I want that phi will be in fact morphism between these two functors and isomorphism between these two functors. Yes. So you can see that the functor is contravariant on x because x is here and covariant on y. So C open. So this is a little bit cumbersome, and also it's very, you have dichotomy. So when I say in category theory we have this bonus that we can define, we have scalar product, so it kind of means that we can define the joint functor. But of course it doesn't have to exist as anything in category theory. If it exists, then it's unique up to isomorphism. One, of course, we'll have to prove this, also not very trivial. And well, easy, as usual. But it might exist, might not exist. You cannot say that it partially exists. So for some objects you can apply it, and for some not. And okay, that's maybe enough. So this is why I don't really like this definition. If you want to find it early in the course before you do your dilemma, then you kind of have to use this definition. But now we have your dilemma, so we can do much more fun. Basically, like in linear algebra, we have map from V to W. The dual map is something complicated that depends on the scalar product, etc. If you want the map from W to D. But if you want that a map from W star to V star, it's something completely free because duality is the functor. And the collection of square shifts is also a two functor from the two category of categories to itself. So what do I mean? Contravariant. So we have F dot C to D. So we have square shifts C, square shift D. So we have here F star. And this is something which is basically completely for fun. So F star of functor, I don't know, alpha. Just do the only thing you can do. It's equal. So sorry, I need to say what is equal to x. So it's equal. You take f of x. because it's the only thing we can do with x in C, and then you plug it in alpha. And as usual, I define a new object and homomorphism is as straightforward as this. So this you have completely fulfilled. But what you have in category theory is that you don't have in linear algebra, say, you always have the unit embedding. See? Yeah, by the way, this notation ICID is not a standard notation in equations. Either say unit embedding or just don't say anything, say represented by functors, the functor represented by the object and some words. And if you compare it with analogy to the linear algebra, then the unit embedding will be like having a map from V to V star, which you actually have because you have this pairing, the home pairing. And now you, so this diagram, of course, is not commutative in any way, but now you basically want to say that you, okay, you can define, okay, let's define, so this is F star, this, let's call it F star tilde. And F star tilde, and this is a kind of very large functor from the category of square shifts to category of square shifts. But you can restrict F star tilde to the category of representable square shifts only, which is basically the same as taking F star tilde and composing it around this category, because this category is just equivalent to D.
Without tilde,
What?
I think.
Tilde is not a standard notation, just wanted to, it's not the actual adjoint functor, because the actual adjoint functor should go from C to D. So this is maybe a better approximation of an adjoint functor. And let's call it F star. This is almost what?
But upper star is a standard notation for pullback factor.
Upper star in some, so if you have map between two objects, but here pullback with respect to a functor, I don't know what it is. This is one of the standard notations to a joint functor. It's not the only one, and sometimes make different things. But just for this lecture, I want to define joint functor. I want to call it F star. So this is not really the joint functor from D to C, so it's not the done deal. But this functor is very similar to the adjoint functor, because this is already a functor from D, but not to C, but to put a shift on C. But now we remember that C basically sits here, embedded here by the level embedding, but we can see about the full subcategory represented. So some objects in D will be mapped to objects that are actually representable, objects in C, and some not. So let's define D. Yeah, I don't know. If representable collection of all objects in D such that f hat star of x is in either group. And also let's choose a representation functor like from ref D to C. Or it's not unique, but it's unique up to unique isomorphism. This is kind of the inverse of the unit limit. And then we can define f star to be f hat restricted to D f hat. So it's not defined on the entire category T, but only on those whose image in C is a possession. And just for good measure, this is still not an actual object in C, but only a representable functor. So let's apply rho. So we can start with the object in C.
Like you can
Indeed.
just annotate D F rep as just image of IC.
Yeah, it is. Of not for IC, no. It's image. No, it's image of IC.
No.
Intersect. No, it's a pre-image under this of the image of IC. And it's pre-image of representable functors IC under this. No. So what you actually do here? You start with an object D. You construct a functor. You construct a functor here. You get a functor here. If it is representable, you construct an object here. Maybe it's not, so maybe your functor is not defined on the entire, defined only on this one, which will be equal to the entire D in many cases. So we will say that the functor has a joint if DFF is just D. And if not, it has partially defined joint. It always has some partially defined joint, maybe the category is still. So what? Now we want examples. Yeah, I don't have a list of examples. And so we'll have to come up with examples on the spot. Yeah, but although I like this definition more, on the intuitive level, it's often better to think about this definition. So something, or maybe something very important that I didn't say. This definition is not symmetric. So F stands here on the left and G stands here on the right. So I think it means that F is called the left adjoint to G, and G is called the right adjoint to F. And of course, you often have very good intuition that some functor have an adjoint functor, and you have good intuition of what it is. And at least me personally never have intuition whether it's left adjoint or right adjoint, and I never remember it, and always have to reconstruct. And so I hope that you will remember this thing better. So when I will give examples, I will we'll never know when it's left adjoint or right adjoint, and it will be an exercise to you to find out, and it's better to develop intuition about it, but we couldn't do it. Probably. And so what is the idea of adjoint functor? And or at least, maybe I will not say the general idea, but if you have a forgetful functor, which usually is a very simple-minded thing, you often have a joint functor to it. And the joint functor, you can think about it as a free addition of the structure. So for forgetful functor, you forget some of the structure, or maybe some of the axioms, and then you can kind of enforce them to work. And this is a free. But you don't know every structure, so you just add it in most naive way, and this is your adjoint functor. So for one hand, adjoint functors give you non-trivial constructions, starting with trivial construction, and for the other hand, they are not not trivial, because you basically do the only thing you can do without any prior knowledge, so the free construction. But of course, sometimes free construction is complex. And sometimes you have two ways, extremes to make this free construction, and then you have to choose between them, and this means that you will have both right adjoint and left. So let's start with examples in this manner. Groups, two sets. I forget the functor. So you probably all know what is a adjoint functor.
Which one?
What?
Which one?
From groups to sets. Left to right. Good question. Nice. No, it's only one of them, I think, in this case, and I don't know which one. But I do know what is the functor. So what is the functor from sets to group? What? Free group generated by a set. Given a set, we can construct the free group generated by a set, just all the words with the letters in this set, like with inverses and with some stupid relations that identities, etc. Okay, let's try to see which one. Given a map between a set and a group, we can extend to the homomorphism from the free group to a set. So if we have S G, this is the homomorphism for groups, is the same as from set from the set S to G, but it's not really G, it's like forget. G is a group, so we need to forget it's a group and then take off. So free is the left, and you see that it will not work that way around. Yeah, so from groups to abelian groups, you have forgetful functor from abelian groups to groups. What is the adjoint functor?
Yes.
Good. Given a group, you groups. Forgetful functor, and here you have the abilization. Abilization functor for any group, you can quotient out with all the commutators, so getting the abilization. My first naive guess was, okay, I know another construction starting with a group and give you that gives you an abelian group, which is the center, and maybe it is with a joint for the other direction. Doesn't work. It's not really a functor, it's center. But you have morphing between groups, that's not necessarily like the center. So kind of disappointing. I would be happy to get the center this way, but doesn't really work. Abilization. Let's take sets and topological spaces. You can forget topology.
Maybe discrete topology.
Exactly.
No, here the answer here it would be important that the answer on the question each
Because you have-
function is one to construct. Like we have two
Exactly.
different functions.
So starting with topological space, you can forget this topology. You get a set. Starting with a set, you can get topological space by taking this topology. But you have another construction. Starting with topological set, you can get another topological set space.
Anti-discrete.
What?
Anti-discrete topology.
You can call it like this, but it's usually called trivial topology. You can just forget take the minimal allowed thing. And they're both kind of free of construction, but two extremes. And one would be a joint for one side and another for the other side. But the trivial topology is like a really bad topology. It's not Hausdorff, but not even T1. So if you want to get T1 topology, very nice, you can do it if you consider the figure of T1 topological spaces. And then we will get what topology? The topology of finite, like the cofinite topology. Topology where closed sets are exactly finite sets. And then that's now, again, something disappointing, you cannot do it for Hausdorff topological spaces. There is just no joint function. For that direction, for the other direction. And what is direction? So basically, any map between a set S and topological space X, any map like this is continuous if you take the discrete topology on S, but it's not continuous if you take some other topology from it. And any map from X to S continuous if you take the trivial topology on X, but it's not continuous in general. So this which the direction side. I can translate it, but I prefer not to put it down. Other examples of adjoint functors. Very nice adjoint functors, which was in this blackboard before the lecture. You have H and G, you have restriction. For those are two groups. For representation G, take finite groups, discrete groups, and here to representation. What is adjoint functor? Induction. Do you know what is the induction of representation? So you can say now you know, just adjoint functor of this functor. Well, you didn't say from what side, so that's a two construction of the induction. And so for general groups, say discrete groups without topology, just groups, they're both well defined. And one of them is a big induction, one small induction, and one is right adjoint, one is left adjoint, who is who. And the idea is that you just start with a representation of H and just force it to be a representation of G. But you change it, you're allowed to change it. So you know how elements of H are, and each time you have an element in G which is not in H, so you don't know how it acts, so you're not allowed to guess something, you just have to take a new copy of your representation. So for each H coset, you have a new copy of your representation. Not for each element of G, because once you have a new element of G, but then another element of H, you know what to do. So you have a copy of your representation for each H coset, and then you have to define how things act. So the correct way to do it is not choosing cosets, but just taking a copy of your representation for each element of G, and then take either subset of this thing or quotient set of this thing, and depending whether you're working from left on the whole line. And so you have small induction and capital induction, which are left and right of the joint to restriction. But restriction is a special case of more general thing. You have a map and you can pull back representations. So now you have a joint functor to the pullback, which are called push forward representations. P. So we have phi of tau, which is pullback of the representation. So any representation of G you can just consider as a representation of H. And then you have phi lower tau and phi lower shriek, and which they are not really very common notations, but I think they are correct notations, which are two adjoints to the pullback of representations. Let's see what they mean in another example. So this was one-to-one map. So the other extreme for one-to-one map is an onto map, and the most extreme case of onto map is a map from say G to trivial. So what is the pullback of representation of a trivial group?
Just forget people.
Not really, because you start with a trivial group and get a representation of G. So you kind of have to add structure.
You asked what the pullback.
But
Oh, sorry.
pullback, not push forward. So kind of straightforward. But
Yeah.
the trivial representation, just you take the same vector space with a trivial action. And then you can ask what is its adjoint. And it's have two adjoints. So we start with the representation and want to get a vector space, but this is not a forgetful functor. Yeah? You want to get something with trivial action. So what will you do? How you make a representation to deal with a trivial action? False. There are two ways to force something to have trivial action. One way, just throw away everything where the action is not trivial. Meaning takes invariant subset. B. Another way, you just say no, you are all invariant. You just don't know about it. So if V and GV are different, so now they're not different anymore. But these are called co-invariants, which are by definition equal to V modulo everything that all expressions that generate that basis. You just kill everything which is not invariant. There's also two different functors. The R is a morphic if your group is finite and the characteristic is 0. Some other cases, but in general they're all different. מה? הערכה?
You read that about B?
V modulo GV V
Oh,
minus
no,
GV.
but the notation.
VG. Like this variance is a coin point. And yes, and in general, if you have any map like this, so if you have any onto map, so you still can consider invariant and co-invariant with respect to the kernel. And kernel is a normal subgroup, so when you consider invariance with respect to the kernel, you still have an action. So if you have a map from H to G, which is a onto, so you can consider invariant with respect to this map kernel, so you still will have an action of H, but the kernel will act trivially, so in fact you will have an action of G. So this is a invariant and co-invariant functors. You can consider them as functors mixed this, and they are dual to the pool. They are adjoining to the pool. And invariance and co-invariance. And if you have a general map, you can always write it as an onto map and then embedding. So then you have composition of this induction and co-invariance. Oh, induction and invariance or induction co-invariance, depending. You have to take the correct induction and pair it with the correct invariance and co-invariance. Do we have other joint functors? Maybe for the next time. Oh no. Oh, okay. Maybe I will say limits and colimits yet again. So limits and colimits, then we have limits. We have like two definitions. Yes, one definition we constructed initial object somewhere. No, terminal object.
Limits is initial, limits is
Yes, it's terminal. Empty limit is terminal object. So we construct as a terminal object. Another definition we constructed, just we have to define four sets, and we do by hand, and then we take the representable functor, the functor that represent, if exists, the limit of the functor that's represented by the term. Now another definition. With the joint functor. So as they say, everything is everything, so we can say that the only construction in category theory is a joint functor, and then you can explain all that construction in this case, in this sense. So you have diagram gamma. Let's see. So gamma is the shape of the diagram. Now we have gamma of D net equals C, which is function of the shape C. And now you have gamma tilde. So you remember gamma tilde, we add to the diagram. I think in this case something at the beginning if you want to do it. Gamma tilde, and we have a natural embedding from gamma to gamma tilde. And now if we so diagrams of shape that gamma tilde, or in other words, functors of gamma tilde. See, you of course can restrict restriction functor. Okay, we have so yeah, we can just forget this object that way. If we have functors one direction, it have a joint functor. It might not have it, it might be partially defined, I don't care. And so I can try to construct functor, a joint functor, I of course don't remember the direction, to the other direction. So and then I can take res star of D. And to it I can plug in any element of gamma tilde, but of course only one will give me something new. So I will plug to it the equal of gamma tilde. Like this. Just add. And this will be, by definition, the limit of gamma of this. Of course, this might be not defined, so we say joint functor, we don't consider it as something that has to be either completely defined or completely undefined. We can ask whether the joint functor makes sense for a specific object, and if it does, then this will be seen. And well, an exercise is maybe cumbersome but not hard to show that this definition of a limit in general coincide with the previous definition. But on the intuitive way you see, level you see it, yes, we want naturally to extend our diagram to edit another object in the beginning. So we take a kind of the free thing that we get, the only thing we can get if it exists, and this is a joint function. Okay, next week. If you want to ask something, I will do that. Just not much.
כן, זה בכל שנה. לא משהו. סלום. סלום. זה אום, אני יודע אפילו זה לא אפשר. גם זה ככה. זה בדרך כלל ציין. אין לי כאן טוב. כל פעם אנחנו סתם.
У меня есть деловое предложение. Пошли есть туда. Нет, Сан-Мартин. Меня не признают, соответственно. Вот это не признали в этом смысле. Подожди, Сан-Мартин. Это вот есть который. Нет, ну не вкусно. объяснить, обоснуть, там не слышно точку. Тут обоснуть. Вот знаешь, вот следующая мастер класса, ну, там не мои. Что-то, что требует объяснения. А где ты, а где ты ешь? Слово P-square. Слово я не люблю ответ. P-square. Или готовлю себе сам. Я это люблю. Просто средство проваливаю еще. И самый простой экспириенс, когда ты что-то хочешь научиться. Ладно, давай, я в сторону. Я буду тебя. Я стал вопрос.
Я не выключу раз хрень. Ну, можно оставить, кстати. Не сказал сказать.